Great, thank you. So credit where this is due. This is a talk of the work by Chad Ostrander, who's a graduate student working with me. He couldn't be here for family reasons, so he asked me to cover his talk. And it's work that he began and has continued with Suni Nielsen at Woods Hole Oceanographic Institution and Jeremy Owens when he was there, as well as with my group. So this thallium work that I'm going to show you here, thallium isotopes, is really being generated at WHOI. This work follows on, it's a sequel of sequels to the whiff of oxygen story that began with this paper in 2007, and a companion paper led by Jay Kaufman that argued based on molybdenum enrichments in 2.5 billion year old black shales, the Mount McRae shale, that there was that this molybdenum enrichments are evidence of trace oxygen in the environment at that time. And subsequent to this paper, there's been a number of other studies, a number of other proxies that all kind of point in the same direction, where the most parsimonious explanation is a whiff of oxygen, small amounts of oxygen in the pre-great oxidation event, the pre-GOE environment. And other studies have extended this kind of thinking back substantially earlier than an extra 500 million years or more. So all of that work has kind of solidified this notion that the pre-GOE environment was not devoid of oxygen, that there was some small amount of oxygen in the oceans, in oxygen oases or other such environments, perhaps emanating into the atmosphere and being rapidly consumed by oxidative weathering. But the outstanding question, we have this kind of vision that is an old vision and has become solidified, but the extent of this oxygenation is poorly constrained. And so this is the question that has really interested Chad, and he started thinking about whether or not thallium isotopes could be useful as a constraint, which is what I'm going to present here or get to. There have been a few other studies that really tried to get at this extent of oxygenation question in the oceans. This work here in 2006 by John Eigenbrod and Kate Freeman made arguments based on carbon isotopes for extensive oxygenation on continental margins, widespread oxygenation before the GOE in water columns and over continental margins. And then in 2010, Brian Kendall used rhenium enrichments, not isotopes, but just concentration enrichments in South African drill cores from about 2.6 billion years ago to make the argument that there was oxygenation down to the sediment-water interface, at least in that location, which promotes rhenium burial and was the explanation for the rhenium enrichments that Brian identified. So there have been arguments made that oxygenation was extensive enough to actually give you fully oxygenated water columns on continental margins, at least in some locations. So that leads to a prediction. You might predict then that if you really did have, at least in some places and times, fully oxygenated water columns, that you would have had the ability to bury manganese oxides in marginal sedimentary environments. The basic idea being simply that in order to actually bury manganese and sequester it in sediments, you need to have oxygen penetration in order to allow for the preservation of manganese oxides during the burial process. If you don't have oxygen penetration below the sediment-water interface, then you get the manganese cycling back out. And so Chad speculated that, well, okay, if these kind of environments were widespread, we don't actually have those sediments, so we have to look for them indirectly, but if these kind of environments are widespread with manganese oxides being buried, perhaps there would be fingerprints of that we could find in isotope systems. Now, we've done some work previously to this with the notion that molybdenum isotopes might be useful for this. And the basic concept for molybdenum isotopes, schematically, is that we know that molybdenum isotopes molybdenum absorbs onto manganese oxides. And there's an isotope fractionation when that happens, such that isotopically light molybdenum is preferentially buried with manganese oxides, leaving seawater heavy as a result. And in fact, modern seawater is shifted substantially heavyward compared to the molybdenum isotope composition of river inputs because of this process going on today, because we have copious manganese oxide deposition on the seafloor today. So if you have environments where oxygen penetrates the sediment-water interface and bury manganese oxides, you should preferentially sequester light molybdenum, leaving the oceans heavy. And you can sample that. You can probe for, in theory, in principle, you can probe for the seawater molybdenum isotope composition by looking at molybdenum isotope composition in sediments deposited under euxinic conditions, at least in those places where the water masses have enough time for quantitative removal of the molybdenum in those environments. And so we and others have pursued molybdenum isotopes with that in mind. This is work by a former graduate student, Yun Duan, in 2010 in the McRae shale. So here's the same thing you saw before, the molybdenum enrichments around 2.5 billion years ago in the Mount McRae shale. Down here you have very little molybdenum, then you have this increase, which is the original signature of this whiff of oxygen concept. And here are molybdenum isotopes, and you can see there's a shift to heavier values here, somewhat correlated with these molybdenum enrichments. And the argument was made that this shift to heavier molybdenum isotope values is indicative of a shift to heavier molybdenum isotope values in the oceans being sampled at this time, and that is due to preferential removal of light molybdenum in oxidative environments, perhaps including manganese oxides at the sediment-water interface in some places. So that was one of the ideas put forward in this paper, but there are a number of ambiguities with molybdenum isotopes. They're also adsorbent to iron oxides. It's not a unique tracer for manganese, and there's fractionation there too. There's complexation of molybdenum with organic matter that can also impart isotope fractionation. And even in these euxinic settings, if you don't have complete removal of molybdenum, there's an isotope fractionation when molybdenum forms thiomolybdates or oxythiomolybdates. So if you don't have complete removal, you can get fractionation even in these reduced environments that are supposed to be where you're getting a good record of the seawater value. So there are a number of ambiguities with molybdenum isotopes that always left a question mark about what that shift to heavy values really means, other than in general that it has to do with oxidation, probably. So thallium isotopes come into play in this way, and this is a slightly complicated system, but I'll try to give you the simple message out of it. So first of all, we talk in terms of the 205 to 203 ratio. It's a very small variation, so it's in epsilon units, 10 to the 4, rather than delta units, 10 to the 3. Thallium comes in from a number of sources: volcanic gases, rivers, hydrothermal vents, aerosols, into seawater. Gets removed primarily into 3 sinks. It gets removed in association with manganese oxides. That's kind of key. It also gets removed during alteration of ocean crust. That's a net sink for thallium from the oceans. And it gets removed very efficiently into anoxic sedimentary environments where you have some sulfide in the water column. The key to the story here is that when thallium is removed into these manganese oxide environments, there is a very strong fractionation, 13 epsilon units here versus -2 in the input, and -6 in seawater. So there's a strong shift, strong preferential removal of heavy thallium into these sediments, leaving seawater light. This is the big fractionation in the system. And in these reducing environments, thallium seems to be very nicely, a very nice recorder of the seawater isotope composition. There does not seem to be fractionation during removal into these environments. These environments, sediments deposited in these environments can be a pretty good probe of seawater. And the seawater isotope composition, we think, should vary as a function of how important this manganese oxide burial story is. And this has been reviewed in this nice paper in Reviews in Mineralogy and Geochemistry. There's been a number of studies building this up by Sunny Nielsen's group and Jeremy and others. Critically, the ambiguities that plague molybdenum isotopes don't plague thallium isotopes. It appears, as far as anybody can tell so far, that thallium isotopes don't fractionate during adsorption onto iron oxides, for example. So that ambiguity that is there with molybdenum is gone. And thallium doesn't seem to form thiocomplexes and doesn't seem to be subject to this incomplete removal problem in reducing environments. And so it's still early days. All new proxies go through their wave of optimism. Maybe we're still there with thallium. But at least at the moment, it seems to not have the same ambiguities in molybdenum. And so the notion that Chad had was, let's go and look, and here's what he hypothesized we ought to see. If you have environments where you have oxygen penetrating the sediment-water interface and burial of manganese oxides, you will preferentially sequester light isotopes of molybdenum, as we said before, and you should preferentially sequester heavy isotopes of thallium. That's what the other data shows. So seawater, in these kind of situations, seawater should be driven towards heavy molybdenum isotope values and light thallium isotope values. And we should be able to probe both of those in highly reducing sedimentary environments. And what you should see then is a complementary shift. You should see these guys going sort of in opposite directions. They should complement each other. So you might expect to see, if you go from a anoxic world to a more oxidizing one, you might expect to see then in black shales, which are this reduced complement to the oxides where we can actually track seawater, we think. You might expect to see then thallium going light, molybdenum going heavy, and microphones getting knocked around and all sorts of stuff like that. So that's what you might expect to see. So what do we actually see then? So this is work that was just published earlier this year in Nature Geosciences. So here is, again, this molybdenum enrichment in the black shales. Here are, I can't even see my own slides here. Here's the molybdenum isotope values. So Chad went and remeasured the molybdenum isotopes at much higher resolution, so there's a lot more molybdenum isotope data now. So you can see this shift to heavier values of molybdenum isotopes, then a shift back down, then interestingly another shift up here. We're trying to figure out what that means. And here are the thallium isotopes, and you can see they mirror, pretty nicely. for this kind of work anyway, of 2.5 billion year old sediments and all the things that have happened since then potentially. There does seem to be this complementarity very much the way Chad predicted, and it's geochemistry, so trends, but this is a statistically significant trend, right? There's a correlation there. So the upshot then is it looks like we would argue that this is at least a strong argument can be made that what you're seeing here is evidence of not just small amounts of oxygen in the environment, but actually a burial of manganese oxides. Burial of manganese oxides to an extent that's significant enough that it's affecting the ocean budgets of both thallium and molybdenum. So you can do some simple isotope mass balance modeling. You can come up with, for molybdenum isotopes, that the fraction of molybdenum in the system that's being removed by the manganese oxides at that time was something like 20 to 30%. For thallium isotopes, it's somewhere between 6 and 20%. Big uncertainties because there's a lot of uncertainties, of course, in the budgets of these elements. But these are pretty significant. They're smaller fractions than in the modern oceans, but not dramatically smaller. They're smaller by 10 or 20% or so. So these are pretty sizable oxic sinks, and so it's hard to turn that into a quantitative measure. That requires a lot better understanding of the budgets, which we're working on. But what emerges more strongly than before is the notion that we might want to be thinking about Archean environments in which the shelf environment was sufficiently oxygenated that you actually had manganese oxides being buried in sediments. You had fully oxygenated water columns down to the sediment-water interface persistently for long periods of time in large parts of the ocean. So when you think about oxygen oases, you might really want to think about substantially oxygenated shelf environments for long periods of time, coming and going and wafting and waning. And so I will end there and take questions. Thanks.
The whiffs of oxygen at these shorelines, is that where you expect the most, cyanobacteria to be producing the oxygen?
It's a reasonable hypothesis.
Is there any other hypothesis?
I mean, if you interpret all this evidence as evidence of O2 production by photosynthesis, then presumably you're talking about cyanobacteria growing in those nearshore environments. It's a very classic idea. It's not a new idea, right?
But there's no land anything.
The land question. Don, sitting right behind you, might have a better idea what might have been on land than I do. But
you have biological soil crusts on your diagram.
Yeah. Do we want to believe it?
I do.
Okay.
So I was also going to ask.
But again, but just get back to the actual story here, right? The thallium isotopes are telling you about burial in the ocean environment, right? So yeah, you could have had oxygen production on land. You could have had the biological soil crust. I mean, I buy it too. But that wouldn't give you manganese oxide deposition very easily in the marginal environments. I think you need to have oxygen actually in the water to allow those manganese oxides to be preserved and buried. That's what the modern oceanographic data would tell you.
So I'll ask you about that last statement. I'm
Okay.
Don Sumner, UC Davis.
Hey, Don.
I'm wondering if you actually need oxygen accumulation in the water, or if you can do this process with oxygen production in benthic mats in these areas. So one of the great things about benthic mats is that you concentrate the oxygen and you can get very high values
Right.
over extensive areas without actually oxidizing the water
Right.
itself. And that oxygen does penetrate into the sediment, especially with low sulfate.
Right. No, I think it's a good question. I mean, obviously that's going to be restricted to a smaller part of the area is going to be smaller because it has to be shallower because light has to penetrate. But we don't have a good enough quantitative, idea
Right.
to really get traction on that. But I think that would be an interesting question.
Right.
Ask how much environment could you
Right. And
cover that way?
We do have benthic mats to hundreds of meters based on the stratigraphy and at least
Right.
the carbonate
That's a good
platform
idea.
areas.
Yeah.
Amelia Hernandez, UC Davis.
Hey.
You've presented a case of a stratified ocean, at least in the nearshore environments. What sort of physical processes are required to maintain the stratification, like such as salinity is presented in the previous talk?
So I don't know how stably stratified all this would have been. These are kind of scenarios that I think would have been coming and going. So I don't think you should be thinking of an ocean that is, for a billion years, oxidized at the surface, euxinic wedges, and things are coming and going and moving. And I think that's what we see in the geologic record, right? We see this molybdenum enrichments come and go. So what do you need? You need to have a dynamic enough system where it doesn't get, stuck. But in terms of, you're asking specifically like what salinity you need to have in the oceans and how would that change things? The dynamics would change if you change the salinity. The rates of mixing would change. So it's a good question.
So,
Where do you want to go with that? I'm looking at Stephanie because I'm thinking of what we might do.
We need to move on to another talk.
Sorry.
Yep. Thank you very much, Ariel.